So for this particular example, we want to look at the function natural log of x, and from it, in between where x is equal to 1 and x is equal to 2, we want to form a solid of revolution. So in other words, a solid that has some kind of volume to it, and calculate that volume. And so here, to start off with, we have a graph of what natural log of x would look like. So I just went and sketched one right quick. And what we want to do here is with this particular area right here, we want to just spin it or rotate it about the x-axis. So if we did that, we would have something like this going on. And with my crude model here, we would have something that would be sort of horn shaped. And so we would take this area, spin it around, and from that it would form a particular shape that would have a volume. And so we want to figure out what that is. Now, in order to calculate the volume, we're going to do the infinite sum of all of the areas, or the area here, and count up all the areas that it would take for us to spin it around the x-axis, and bound it by when x is 1 and 2. And so this would be how we would actually find the volume. Now the question is, well, what is a of x? Well, we learned, if you've watched some of my previous videos, that this would be how we would characterize the area. And so the blue area here is solid, and it just lines up perfectly with the x-axis here. We don't have anything that has a gap or a little strip in it, so we could use the disk method in order to figure out what this area would be. And so the disk method says that we're going to look at this area here as a sum of disk and just add them all up. So that's what the infinite sum here means. And so we know that disk look like circles, and the area of a circle is pi r squared, where r is the radius. So here that would mean that area would be pi r, or radius, squared. And we know the radius of our shape will change as natural log of x changes. So that would imply, if we replace the radius with natural log of x, then we would have pi times natural log of x squared as the area. So now that we know what we're working with, we know what we need to evaluate. So we do the integral from 1 to 2 of pi natural log squared of x dx. So this is the integral that we need to figure out. We pull out our constant, and now you see we have the pi times the integral of natural log squared dx from 1 to 2. Now, if you've watched my previous video called Integration by Parts, Example 2, you'll see that we actually did handle, or did do, the problem of figuring out what is the integral of natural log squared dx. So please review that video if you haven't seen it. If you have, then you know that the indefinite integral will be x natural log squared of x minus 2x natural log of x plus 2x. And so since we're doing a definite integral from 1 to 2, we want to take this piece and evaluate it from 1 to 2. So now we're going to plug in 2 first. And here, if we plug in 2 here, 2 times 2 will be 4. And same thing here, 4. And so now we'll close this up. And now we will do the same thing, but now just plug in 1. And so let me go ahead and clear out some of this work here. All right, so now that we got that cleared, let's go in and evaluate this expression again at 1. So this is 1 times natural log squared of 1 minus 2 times 1 is 2, natural log of 1 plus 2 times 1 is 2. And so we notice here, we know that natural log of 1 is 0. So this particular term turns to 0. This whole term here will turn to 0. And so what we have left here would be 2 natural log squared of 2 minus 4 natural log of 2 plus 4. And then here we'll just have minus 2. And clean that up. We see that 4 minus 2 is 2. So that would be, just rewrite all of this here, plus 2. And so if we put that into our calculator and evaluate it, we would get approximately 0.5916 cubic units. Okay, so again, in order to find the volume for the solid revolution that is formed by taking this area and rotating it about the x-axis from 1 to 2 here, we see that what we would do is imagine that this is a disk and stack these disks with different radii all the way from when x is equal to 2 to x equal to 1, which is represented by this particular integral here, definite integral. And so we knew from a previous video, the one that's titled Integration by Parts, example 2 that I've done, we know what the indefinite integral of the square of natural log is, and so we use that here. And so we leverage that in order to make the problem a little bit shorter. And then from there we just evaluate from when x is 2 to when x is 1, and we finish up the problem. And this concludes this particular example.